All right, welcome back to The Explainer. This week, OpenAI did something we haven't seen in 5 years. They actually dropped a new open-weight model. It's called gpt-oss, and it gives us this rare, fascinating peek behind their curtain. So let's break down what's new, what's different, and why it really matters.
To really get how big a deal this is, we've got to rewind a bit. I mean, you have to remember, back in 2019, GPT-2 was an absolute game changer. It was the model that really showed the world just how powerful and scalable this whole transformer thing could be, pretty much setting the stage for everything that's happened since.
But then, right after that huge breakthrough, OpenAI went radio silent on the open model front for 5 whole years. And in that time, you had GPT-3, you had ChatGPT, they were changing everything. But the code, the weights, totally closed off. So you can imagine why this long wait makes the release of GPT-oss such a big deal for everyone. And that, right there, is the big question we're tackling in this explainer. So what exactly did they cook up in all that time? What are the key upgrades tucked away under the hood? All right, let's get into it. Okay, so first things first, let's set a baseline. We're going to hop in a little time machine here, put the classic GPT-2 right next to its brand new descendant, just to see how much has really changed. Yeah, this timeline really drives home just how long that 5-year gap was. You know, after GPT-2 dropped in 2019, we got these little breadcrumbs, hints of new stuff like sparse attention in the GPT-3 paper. Then boom, 2023, Llama comes along and makes things like rope the new standard. And all of that innovation, all those little steps, have led us to what we're looking at inside GPT-oss today.
Wow. Okay. This table just lays it all out, doesn't it? The sheer scale of the evolution is staggering. I mean, just look at that jump in parameters. But it's not just about size. If you look under the hood, you can see that pretty much every single core part, from how it pays attention to how it keeps its math in check, has been completely swapped out for something newer and way more efficient.
All right, let's get into the nitty-gritty. We're going to walk through the most important upgrades one by one and really see where this new model gets its power.
Okay, first up, a really big one. How does the model even know the order of words in a sentence? The old way was kind of clunky. It had to learn a totally separate piece of data, a vector, for every single position. The new way, rope, is so much more elegant. It actually encodes the position by mathematically rotating the data itself. It's like weaving the word order right into the fabric of the calculations. So why the switch? Well, it's just a smarter, way more efficient solution. You're not just tacking on extra baggage for each word's position, you're building it right in. And honestly, this basically became the industry standard after the Llama models showed everyone just how well it works.
Next up, let's talk about attention. You know, the absolute heart of any transformer model. The old method, multi-head attention, was like giving every single worker, every attention head, its own full set of tools. Kind of wasteful. The new way is called Grouped Query Attention, or GQA, and it's way smarter. It has the heads share their tools, their keys and values, which saves a ton of memory and compute.
And the payoff here? It's huge. GQA means less memory gets used, and inference is just plain faster. And get this, here's a little tidbit from the release notes that blew my mind. It turns out OpenAI was already using a version of this smarter attention, a kind of sparse attention, all the way back in GPT-3 in 2020. They were way ahead of the curve.
All right, the next couple of upgrades are all about efficiency tweaks. It swaps out the old workhorses GLU and layer norm for their faster, leaner, modern cousins, SWIGLU and RMS norm. They do the same job, basically keeping the model's math from going haywire. They just do it a whole lot faster. Let's zoom in on SWIGLU for just a second, because it's pretty clever. It takes a standard part of the network and replaces it with this more complex gated structure. Now you'd think, okay, more layers, more parameters, right? But nope. The layers themselves are actually smaller. And the result is you get better performance with fewer parameters, all because the design itself is just more expressive. It's a perfect example of that work smarter, not harder idea. And that brings us to the final monster upgrade, the Mixture of Experts Architecture, or MOE. This is a total paradigm shift. Instead of one ginormous network trying to do everything, you've got a whole team of specialists, or experts. So when a piece of information, a token, comes in,
This router looks at it and says, okay, you 4 experts over there, this one's for you. What this means is the model can be absolutely massive in total size, holding way more knowledge, but it stays super fast because you're only ever using a small slice of it at any one time.
Okay, so we've seen how we got from GPT-2 to here. But how does GPT-oss actually stack up against the competition today? Let's put it head-to-head with another top open-weight model, QN3, because they take really different paths to get to a similar goal.
Okay, what I find fascinating about this chart is how it reveals 2 totally different design philosophies. You can see it immediately. QN3 goes deep, stacking up 48 layers, or blocks. GPT-oss, on the other hand, goes wide and shallow. It only has 24 blocks, but the pathway for data inside each block is much, much bigger. And they even handle their experts differently. GPT-oss uses fewer but bigger experts, while QN3 has a whole army of smaller ones.
Let's think about it like you're building a brain. GPT-oss is going for a wide brain. It has fewer layers, but each one is really powerful and complex. And that kind of design is awesome for doing a lot of things at once, parallel processing, which makes it really fast. QN3, on the other hand, is building a deep brain, lots and lots of simpler layers stacked up high. This can give you more flexibility, but it can also be a real beast to train. It's a classic engineering trade-off, really. Okay, we've been deep in the weeds with the technical specs, but let's pull back. What does all this stuff actually mean for someone trying to use it? Why should you care? What's the real-world impact?
This single number right here, it says it all. 1. Because of a really clever optimization, the massive 120 billion parameter version of this model can run on just one GPU, a single one. That is an absolute game changer for accessibility. It puts this incredible power into the hands of so many more people.
And check this out. This is another awesome feature. You can actually tell the model how much effort to put into an answer. You can see right on this chart, when you ask for high effort, the accuracy shoots up. This gives you, the user, a brand new dial to turn, letting you trade speed for quality on the fly, depending on what you need. All right, for our conclusion, let's zoom all the way out. What do these design choices in GPT-oss tell us about where AI is heading? Well, first off, it's clear that open-weight models are catching up, and they are catching up fast. Sure, a closed model like GPT-5 might still be a little bit ahead, but look at how close GPT-oss and QN3 are. They are nipping at its heels. That gap between the top-of-the-line secret sauce models and what's available to everyone is shrinking, and that is just fantastic news for the entire field. So what's next? This quote from Dr. Rashka's analysis really frames the central debate perfectly. See, GPT-oss was trained heavily on things like math and code, problem-solving skills, and apparently that came at the cost of some of its general knowledge. And that leaves us with this final, really thought-provoking question about the future of AI. As these models get better and better at pure reasoning, at thinking and using tools to look things up, do they even need to waste their brain space memorizing tons of facts? It's a really fundamental choice. Are we trying to build a massive library, or are we trying to build a machine that can actually think? What do you think is the right path forward? Let us know. We'll see you next time on The Explainer.